let's talk about gravitational potential energy now. And we've already touched on this a few times, right? But the few things that we need to emphasize. So we've already seen this equation, right? That it's mg times y. That's the gravitational potential energy. And you can see it exclusively depends on the height, right? And y, right, is the position of the vertical position of an object, right? So there's one thing about gravitational potential energy that's important, and that's the reference level. It always depends on what reference level you're talking about, right? Now, for example, right, this person walks. If you take 2 points, right, in a gravitational field, and you take so for example, this person walks this path or this path, right? The change in gravitational potential energy is the same. Right? It's independent of the path, and that's what we've talked about in the previous video. But again, the reference point is important. So let's say that you have a table over here, right? And you put a box over here. Right? Now you raise this box to a height h. Now the gravitational potential energy stored in this object, you'll say, okay, because this is your reference point. So let's say that this is R1, right? And this is, let's say, the floor. So now this is your reference point. If you drop the object, the object is over here, let's say, and the energy stored is mgh, right? Now if you drop the object, you get that energy back in terms of kinetic energy. Okay. Now, but instead, if you raise it to this height and you take it to this point, right? Now your reference point has changed. Your reference point becomes this R2. The floor becomes your reference point. And now the energy stored is not going to be mgh, it's going to be mg whatever this height is, right? Mg, let's say h2, right? Let's say this is h1. So by a slight modification, right? If your reference point changes, your potential energy changes. So again, let's say you're in a building, you're in your room, you're jumping in your room. Let's say you jump in your room. Right, your reference point is the floor of your room, right? Obviously, you have a lot more potential energy with reference to the ground that is outside your house. Let's say through the window, right? Obviously, you don't want to jump off the window, but you're gonna get much more energy if you jump off the window because for that reference point you have much more energy, but you're just gonna jump with reference to your room's floor. So in that room, your reference is the floor. Outside, the reference is the ground, right? So the reference point is important, and that's why I wanted to emphasize on that. And we've already seen this situation, right? So if let's say you have a box, you're moving it straight down, the work done is going to be positive because your displacement is down, the force of gravity is down. So they both are in the same direction. The work done is going to be positive, but delta U is going to be negative because let's say if you move from this point, let's say this is h, y equals h, and this is your final point. This is initial. This is y final is 0. So this is your initial point, this is your final point. So you can see that delta y is 0 minus h, and it's negative h, right? So therefore delta u is going to be minus mgh, right? So delta u is negative, whereas work done is positive. And similarly, if you have the opposite situation where you're moving up, then gravity is down, gravity is down, the displacement is up, so displacement is up, gravity is down, so they're in opposite direction. Work done is going to be negative because again of that 180-degree angle, and delta u is positive because y final is h, y initial is 0, so h minus 0 is h. So that gives you positive delta u. So that's the relationship that we've talked about, that it's always going to be true that work done by gravity is always going to be equal to the negative of the change in potential energy, because it's a conservative force. Now let's answer a few questions about gravity. So you have these four balls that are in different situations. So some of them are moving. So the green arrow shows the direction of motion, and then they're at different heights. 2 and 4 are at the same height, right? So you have to rank these based on their gravitational potential energy. Pause the video, think about it. So the answer is D. You can see that they're at the same height. So it doesn't matter what their kinetic energy is. We're talking about the gravitational potential energy, which exclusively depends on the height. So 3 is at the greatest height, so its potential energy is going to be greatest. 2 and 4 are at the same height. Their potential energy is going to be the same. And object 1 is on the ground, which is the lowest potential energy. Okay. Let's answer one more question. So you have 2 balls that are at rest initially, and they roll down a steep hill. So the steepness is obviously different, but the height is the same. The height at which they start is the same. So what do you think is going to be the ball which is going faster at the bottom? So you have to think about which one is going to be faster. So think about energy conservation. Think about we're assuming no friction involved. So mechanical energy is kinetic plus potential. So think about energy conservation. If there's no friction, mechanical stays constant. Right? Now apply conservation of energies. This is your initial point. This is your final point for this ball. This is initial. This is final for this ball. What is going to happen when you apply conservation of energy? And think about the answer. Pause the video. Okay, so the answer is they're going to be the same speed, and that's because of energy conservation. It doesn't depend on the height. So if let's say this height is h, let's call this h. Now if you apply conservation of energy initially, since the ball starts from rest, the initial energy is mgh, right? And the final energy is, so this is our zero of potential at the bottom, the potential energy is 0. It only has kinetic energy, right? So that's half mv squared. So from energy conservation, total energy stays the same, which means, let's say that if this guy has 10 joules of energy over here, its total energy stays 10 joules, right? So that means that mgh is going to be equal to half mv squared. The mass cancels out. So interestingly, it's independent of the mass. So even if the masses of the balls are different, they're going to end up with the same. If you rearrange the equation, take the square root, it's the velocity is going to be square root 2gh. So both of these would have the same velocity at the bottom, and that depends on this height h. If h is the same, the velocity at the bottom is going to be the same.